Greetings, Calc 2 students. This video is for section 7.3, trigonomic substitution, and I want to go over the table of inverse substitutions. So we have the situation of the constant first squared minus the variable squared underneath the square root, or the variable first squared minus the constant squared underneath the square root, or doesn't matter which order, the variable squared plus the constant squared underneath the square root, where the a constant is bigger than 0. So those are the three situations. So the first situation with a squared minus x squared, the constant is first. We use the substitution x equals a times the sine of theta. Now remember, these substitutions have to be an inverse function, and inverse functions are required to be one-to-one. So I'm going to restrict the domain of this function, specifically with the sine being restricted, by restricting theta to be between minus pi over 2 and pi over 2, including those endpoints. The second situation is where I have the variable first squared minus the constant squared underneath the square root. In this situation, I'm going to use the substitution of x equaling a times the secant of theta. But I need to restrict that function so that it becomes one-to-one. And I have some choices, so I can restrict this to be between 0 and pi over 2, not including pi over 2. Or I can restrict it from pi to 3 pi over 2, not including 3 pi over 2. And then finally, I have the situation with x squared plus a squared underneath the square root. And in that situation, I'm going to use the substitution x equals a times the tangent of theta. And again, I must restrict the domain of tangent to make this a one-to-one function, and I'm going to restrict tangent to be between negative pi over 2 and pi over 2, not including the endpoints. So what I would like to do is work out how each of those three situations simplifies to our benefit. So let's do the first one. A squared minus x squared, take the square root. Now that equals, with a suggested substitution, a squared minus a times sine of theta squared, all underneath the square root. Then that becomes a squared minus a squared times sine squared of theta underneath the square root, which becomes, if I factored out an a squared, 1 minus sine squared of theta. Then using Pythagoras' identity, I have a squared times the cosine squared of theta, which simplifies to a times the cosine theta, take its absolute value. But since we have restricted the domain of x, with theta being between negative pi over 2 and pi over 2, that means that this theta is restricted from negative pi over 2 to pi over 2. And the cosine of theta on the interval negative pi over 2 to pi over 2 is always positive, so we can make this even simpler by saying that has to be a times the cosine of theta. Okay, let's take a look at the second one on our list, which is this x squared minus a squared, all underneath the square root. So for that situation, I have x squared minus a squared underneath the square root. And we're going to use the situation where we're making x equal to a times the secant of theta. So a times the secant of theta squared minus a squared underneath the square root. So this is a squared times the secant squared of theta minus a squared underneath the square root. And again, I'm going to factor out an a squared, and I'm left with secant squared minus 1 underneath the square root. And using Pythagoras' identity, that becomes a squared times the tangent squared of theta. I end up with a times tangent of theta. Now once again, I have to worry about this tangent of theta and whether or not it's positive or negative. But because I restricted this to be between 0 and pi over 2, that was my restriction, or between pi and 3 pi over 2, well, that means that this tangent of theta will always be positive. Okay, let's look at the last one. The situation of x squared plus a squared underneath the square root. So I have x squared plus a squared underneath the square root. So using the suggested substitution of x equals a times tangent of theta, I have a times the tangent of theta squared plus a squared. And that becomes a squared times the tangent squared of theta plus a squared. Again, all underneath the square root. And I'm going to factor out an a squared, and I get the tangent squared of theta plus 1 underneath the square root. And using Pythagoras' identity, 1 plus the tangent squared of theta is secant squared of theta. So I get a squared times the secant squared of theta underneath the square root. And then that simplifies to a times the secant of theta. And once again, I have to deal with the fact that I would need an absolute value symbol here. However, because of the restriction, I have theta lying between negative pi over 2 and positive pi over 2, and secant on that interval is always positive. This section deals with these type of integrals, and these three different expressions with this clever substitution can be simplified so that we transformed a function of x into a function of theta, and it is easier to deal with that simpler integral.